Well, thank you, and welcome to the last panel of the day. Congratulations for making it through an incredible program that has talked a lot about how robotics are going to change our economy, how robots are going to change how we live. So I think it's very appropriate that the last panel of the day focuses on how robots might help save lives in disasters or in other very extreme situations. To talk about that, we have a really well-rounded panel in the sense that we have a representative from each part of the ecosystem that will matter for how robotics comes to be used by first responders in disaster situations. To my left, we have Masato, who represents Mitsubishi here in Silicon Valley, who is a major player, of course, in robotics and advanced electronics. We have Melissa Ho, who runs a really unique program for the Department of Homeland Security that acquires technology for use by the federal government. We have Yusuke, who in his role at NEDO is a sponsor of this ecosystem, a sponsor of a broad swath of research and development. And then last but not least, we have Allison, a professor of mechanical engineering at Stanford, who is at the forefront of some of the next generation technologies that we'll see in robotics. So to reward you for making it through to the end of the day, we're going to do something a bit different with this panel. We're going to have a bit of show and tell. We're going to have 3 short presentations. We'll then have a conversation amongst ourselves up here, and then we'll open the panel to questions. So with that, I would love to introduce Masato to go first and talk about some really interesting robotic applications in the nuclear space.
My name is Masato Iehara, General Manager of our Silicon Valley office. Actually, this is my, thank you very much for inviting to this great opportunity, and I'm very glad to be here. And I will explain a little bit about what we are doing about robotics earlier. And actually, I think I already sent a presentation. Before presenting our robotics activity, I have to mention a little bit about what the Mitsubishi is. So I hope that many of you know the Mitsubishi. However, its structure is a little bit complicated. So Mitsubishi is just a brand. So that means I'm from Mitsubishi Heavy Industries. And Mitsubishi is also used in Mitsubishi Motors, Mitsubishi Electric, Mitsubishi Bank. So basically, we are all independent companies to each other. In that sense, we are a manufacturing company only for heavy machines, like power plant, airplane, train system. And we are the biggest defense contractor for Japanese government. So in that sense, we are doing the robotics activity only for special robot, not for industrial robot. And I will explain a little bit about our robots about nuclear power plant.
Do you have any luck finding Masato's slides by chance?
No.
No slides. Oh boy. Okay. Well, maybe while we're looking for them, why don't we go slightly out of order here and have Melissa talk a little bit about her office and its unique mission, and the hopes that we can come up with the slides for both Masato, Yusuke, and then Allison.
Sure. So just to give folks a little bit of background, as Chris mentioned, I'm based here in Silicon Valley with the Department of Homeland Security, and my primary focus and mission is actually to reach out to the startup community and identify where there's commercial technologies that startups are working on that have complementary and very common alignment with some of the Department of Homeland Security's mission spaces as well. We want to focus on actually getting commercial technologies in place. So my program actually funds startups that are early stage, working on a commercial product that has application to some of the problem sets and use cases that we've put out there, which include first responders, cybersecurity, border security, a number of different mission areas where we are interested in funding those companies. And we fund up to 800,000 over 4 tranches, non-dilutive, and actually provide opportunities for startups to work closely with end users, iterate on their products, and actually have potentially a new market that they're interested in pursuing. As the investment panel I mentioned before, we're able to actually provide a customer to those startups and be able to allow the companies to find a product market fit and determine whether or not their commercial product aligns with a government use case as well. So that's what my program is primarily focused on doing. And as Chris mentioned, we're part of sort of the end user community, but at the same time recognizing that we, the government, need to offer funding to help with that product development. So we're not interested in taking IP, we're not interested in taking equity in the companies. And so I think it's wonderful that this conference is here looking at where robotics is happening and where there may be opportunities for the government to take advantage of some of the interesting innovations that's happening in the robotics space. For example, we have funded actually some drone companies, not the platforms themselves, but actually capabilities to enhance consumer drones, such as platform security, sensors, and automation, and recognizing that there's a market in the critical infrastructure space that aligns well with what we're looking for from our own search and rescue mission, whether it's the Coast Guard, whether it's first responders, whether it's Border Patrol. So that's what we've been looking at doing within our program, and if anybody's interested in looking at what opportunities we have out there, just Google DHS Silicon Valley Innovation, and you can find some of the funding opportunities we have.
Yeah, I'd say that Melissa's home department, the Department of Homeland Security, is uniquely broad in its mission set and probably encompasses almost every use case you could imagine for a robot in a disaster relief situation or a security situation for that matter. Well, if we don't have any luck on the slides yet, I'd say we might have to do this the old-fashioned way, even though we tried hard to do a little bit of show and tell. And maybe I'll just ask Masato to start with a bit of a description of the role of robotics in the nuclear space. And maybe if we're lucky, as we go forward, we'll come up with some AV here for everybody.
Sure. I will describe our robotics activity as possible. And yeah, actually we are the very big nuclear power plant manufacturer in Japan. Almost half of nuclear power plant are our products. And our history for nuclear power plant robots is almost 40 years or something like that. That robot is mainly for maintenance and inspection in very harsh environment. That means that it's a high radiation area or underwater or something like that. So we have underwater inspection robot or kind of repairment robot for very high radiation area. That robot is not just visual inspection, but do a kind of physical task. That is our capability. And robots for nuclear power plant requires a special technologies, not only for anti-radiation, but for it should be washable or decontaminatable or something like that. So we are very good at making that kind of special robot. Yeah, sometimes it could be very expensive. However, yeah, actually we are very good at that kind of special robot. And recently, we are now trying to expand this kind of business into other fields, like oil and gas industries, chemical industries, maybe other industries. In that sense, that kind of special robot is still very important for example, very high explosive environment or hazmat environment. So we would like to explore that kind of special robotics market. And eventually, that kind of technology can be easily transferred for search and rescue market. Mm-hmm. So in that sense, we are exploring inspection or maintenance robot for special purpose and search and rescue robot. That is our activities, right?
Well, thank you for that overview. And why don't I now turn to Yusuke, who can talk a little bit about the really broad spectrum of projects that NEDO is funding in the robotics and disaster and infrastructure survey space.
Thank you, Chris. And I'd like to talk with my slide. Thank you. Good afternoon, everyone. I'm Yusuke Yasukawa from NEDO, and I'm a project manager of the title showing here, a long title, Robot and Sensor System Development Project for Infrastructure Maintenance and Disaster Survey. And our goal is making a system for social infrastructures. And we have two areas for that. The first one is for infrastructure inspection. The next slide, please. Here is the first area, the infrastructure inspection. And one system is making sensors for continuous sensing for the bridges, or developing inspection robot for the tunnels or dams. But this area is not fitted to our subject. The next slide, please. Next slide. Yes, thank you. And the second area is we are developing a robot for disaster survey. In Japan, I'm from Japan. In Japan, there's recently so many disasters. 2 days ago, we have a new volcano eruptions at the Kyushu area, or the tsunami, or landslide. Recently, the climate is very changing, and we have many disasters. Then we decided to make a special robot for these disasters. Then we have, in this project, we have 3 kinds of robot for these disasters. From our next slide, I have prepared 3 slides, and I will introduce 3 robots today. Thank you. The first one is an anti-explosive robot. This robot is used under the flammable environment. Like in the tunnel accident, there may be fuels from the cars. It's very dangerous for the explosion. Then this robot is used at that environment, and this robot is not cause of the explosion. But this robot is developed by the Mitsubishi Heavy Industries, and maybe Iehara-san is fit to explain it.
Actually, this is the exactly one I would like to explain.
We got it up after all.
And this robot has a certification of the this is the first robot has a certificated robot for the anti-explosive teleoperation robot. The next slide, please. The next robot is for volcanoes. In the left slide, next picture, we can see the volcano eruption. But the danger in the volcano is not only the eruption. After eruption, we often have ash flow from the volcanoes. In the eruption, there is so many ashes from the sky, and when we have rains, the ash is flowing down like a river. It's very dangerous for the houses in the mountain footage. Then we are developing yes, a multi-copter robot for the inspecting the ashes. In the right pictures, we can see the robot inspection. The first one is the 3D mapping. You may know that a drone can measure the three-dimensional features, land features. And the middle pictures shows the sampling devices suspended on the drones. The lower picture, we can see the perimeter. It's a water absorption of the ashes, we can measure by that devices. Using that sensors, we can simulate of the ash flow. Then we can make an alarm for the footage houses. That's a robot for the volcanoes we developed. Next slide, please. The last one is sensors for finding vehicles in underground. In the landslide, the automobile or something like that may vary in the underground. The sensor, it's an electromagnetic search system, is suspended by the drones. It's finding those kind of ions, and then we can find a person in the cars underground. Then that's all. Fine. Thank you.
Thank you, Yusuke. It's amazing to see from his slides the breadth of potential applications in this space, and also just the complexity and difficulty that are a part of each of those environments. We're now going to turn to Allison for a peek at the future of what technologies might be coming down the road. And if we're lucky enough to get her slides up on screen, we might see a snake.
That's right. Thank you. So I'd like to talk a little bit about soft continuum robots for search and rescue and disaster scenario applications. I believe there's already been some discussion today about soft robotics and their potential, but these applications in these very rough, harsh, unstructured environments, soft robots might not be the first thing that you think of. Before I show some of our work, I just want to acknowledge that Japanese researchers are really the leaders in the field here. There's been extremely impressive work in terms of making long, thin continuum robots that can get deep into places that are difficult to access. The challenge has been making these things reliable in very unstructured environments, and then also being sure not to actually cause more damage in the environment that you're operating through. So the needs in this area in terms of close-up interaction and manipulation have been about access, delivering water or air, and even being able to manipulate in really hard-to-reach areas. And so the figure at the bottom, the image at the bottom, is representing a new technology for soft robots that we call vine robots, which attempt to grow in the way that a plant grows. And the way this is achieved is actually amazingly simple. You take a plastic bag, a tube, and you fill it with air, and you can push more tube through the center of the material and allow it to extend. And it turns out you can extend this for hundreds of meters. There are other robotics researchers who have done similar things, including making these kinds of toroid water snakes. If you're having trouble how it pictures, if your kid has a water snake toy, it is a very similar concept. So the kinds of things you can do with a robot like this is deliver it in a really compact form to a disaster site and then be able to grow it simply by adding pneumatic pressure. It can go up and support its own weight for quite a ways before it buckles, and like I said, it can also go hundreds of meters in length. So the key is what can we do to actually make it a robot and not just grow it? And so there are various ways in which you can change direction. For example, pinch plastic on the sides in order to turn it left or turn it right, or have additional pneumatic or air-driven actuators along the sides that can get it to steer. And so this is where it starts to look a little more like a snake and maybe even a bit creepy. But when you see the applications, I think you'll see what kind of advantages this sort of actuation technology encompasses. It can go over water. We have grown these into antenna that can change their shape, for example, to reach different frequencies and be able to change on the fly. They can pop through holes, which are much smaller than their own body's diameter, and they can go through a lot of environments that a classic snake-like robot wouldn't be able to go, such as one where they even get punctured on the side through nails, which is shown in the video below. And it can keep going as long as new material can get fed through the center of the robot. And then this is the last slide coming up with just a few more applications that kind of push the cutting edge of what these robots can do in some search and rescue type applications. The video on top shows a mechanically pre-programmed vine robot that's growing and then hooking around a valve that might have, say, a gas leak in a disaster scenario. And then by wrapping itself around objects and then pulling from the base, the robot can actually do some simple manipulation tasks. And as we push the technology forward and make these actively controllable, we might be able to reach, manipulate, do things at long distances that we can't currently do today. We can also do things like feed cables through the ceiling of our lab and do a simple firefighting application. So the lower right shows a robot that feeds water and air and grows through the center like the others, but then when it gets over the fire melts the plastic, and then the water and air come out and actually put the fire out. So this is a new type of robot. There are many other types of interesting new developments in robotics. The thing I want to emphasize is there's a long, long way from developing these things in the laboratory to the kinds of applications that some of my co-panelists are actually demonstrating in the field and in real disaster scenarios. But in academia, as we push the envelope for these kinds of technologies, we're going to start seeing that transfer. And it's through the support of agencies like Homeland Security that can support that transition and kind of get through this valley of death from getting from the laboratory to these really difficult applications. Thank you.
Allison, that's just amazing technology. I wonder if has it ever showed up at a graduate student party at Stanford in addition to a laboratory situation?
Yeah, we've had some grow around arms to the surprise of people. Yeah.
To follow up on how you ended your presentation, you alluded to the challenges that we're going to face taking this amazing cutting-edge technology and introducing it into real life or death situations in complex environments. Could you say a little bit about what you see as some of the big technical hurdles and maybe opportunities, at least for the technology that you're working with in your lab?
Well, in addition to the kinds of basic mechanical problems in terms of how do you design such a robot and how do you sense with it, I think the bigger technology questions are how do you actually use it? We were discussing this in the green room beforehand about the trade-offs between autonomy and human-in-the-loop control. There are going to be many scenarios where the user needs to have a very good situational awareness of what the robot is doing and have these sort of perceptual capabilities of the robot transmitted to them. And that's going to be essential in some very difficult and challenging situations in the field. But on the other hand, users are going to be trying to manage a lot of different things and multitasking. And so there's also a need to make aspects of these robots autonomous and deal with the very unstructured environments and uncertainty that they encounter in the field. So understanding this trade-off between autonomy and human-in-loop control and making those optimal so that a non-expert user in the field can go and deploy them is really going to be the next frontier now that we are starting to get the robots themselves.
So drawing on your point that field experimentation is going to be crucial among the just many, many different user communities and potential applications, I would love to ask Melissa and then our other panelists what you see is what are some of the communities that are really forward-leaning and maybe what are some areas of opportunity where we have communities and technology but they're not connected in the way that we might hope yet?
Yeah, definitely, and I really appreciate what you mentioned, Allison, because from the end user standpoint, you know, the desire and use of to use technologies to make the mission to solve mission problems more efficient and easier is complicated a bit by the fact that there is more technology and there is more use, and we have agents in the field that need to both perform search and rescue missions while at the same time avoid being in the adversary's crosshairs as well. And so some of the more forward-leaning agencies that I've seen looking at some of these robotic technologies is Customs and Border Protection, particularly the Border Patrol is looking at the use of some of these consumer-based platforms to help them as they're performing search and rescue missions. They have to, in many cases, be in very rough environments, and so it seems only natural for them to use these types of technologies to sort of be a sort of like forward deployment, be able to go look for potential people who are in need or and in danger without putting themselves in danger as well. And so I actually really commend within the Department of Homeland Security, our Border Patrol agents are doing a lot to try and help with search and rescue and looking at new technologies to help them with that space. Certainly, first responders are looking, just through my interactions with a number of the different first responder communities around the country, a lot of fire, rescue, and police are looking at how do they properly, with certain privacy controls in place, use these types of technologies. And certainly there are a lot of challenges associated with regulatory use and privacy that everybody is facing, but certainly a lot of the first responder communities are trying to see how they can use these types of technologies in a much more efficient manner. And so it's very encouraging to see that, and I encourage those first responders to take a look at some of the interesting robotic applications that we just saw here on the panel.
I'll ask a question, I guess, for the whole panel, but maybe in particular to Yusuke and Masato. This is a complicated ecosystem we're talking about here. There are many different funding bodies. They're funding a spectrum of research. There are large and small companies, and then there are many end users of robots in this space, both at many different levels of the government. Is this ecosystem coalescing? Is it coming together? Are there ways that the different parts of it could be working better together to realize the potential promise in this area of robotics?
Yes. The main key is autonomous, I think. Allison says the autonomy. And but in the disaster environment, it's a very complicated environment. Using autonomy is a little bit too complicated environment. And a former robot we used teaching playback control as the industry robot. After that, we use autonomous systems. As traffic, it's we can use we are now development of autonomous system. But autonomous car, it's an environment. The road is model. We can make a model. It's the road is flat places and other side of the road there is houses like that. But in the disaster environment, we can't make a model. It's very complicated. Then it's very difficult to make an autonomous system for that. And the key of the robot of the disaster system is, I think that we make a collaboration system of human and robot. The big decision will made by the human operator, and but the human operator will exhausted using teleoperation in the long time. Then the robot can support the human operator. Then the partial autonomous system in the small area of the disaster environment, we can make robot itself, but the global judgment, global decision is made by a human operator. That is, I think, a good system for that kind of robots.
Yeah, from industry point of view, it is very difficult to make a business model around robotics other than nuclear power plant robot. And actually, we have two difficulties. One is the technology side. Another one is the business side. The technology side, we are very open to apply the technology from including startup companies. That's why I'm here. Actually, I'm based in Silicon Valley and looking for technologies around here that can be applied for not only for our robot, but also for our product or our service, entirely our service. And obviously, robot is not one technology. It's a system integration. That means we need a lot of great technologies. And actually, we are very good at integrating that technologies into one robot with industrial quality. So system development side, yeah, we can develop probably literally any robot that our customers like. However, to make it a business, we need customer and we need sustainable business model. And actually, as for the search and rescue robot, the customer would be kind of government, local government, or maybe utility companies or something like that. So it's not, obviously, it's not a sustainable business. So how to make it a sustainable business, it's a very difficult. And definitely we need maybe government support for R&D until we make it a sustainable business.
I'll just ask one last question of my fellow panelists, and then we'll move to open questions to the floor. So get ready to come to the microphones and pepper us with tough questions. And so my final question to the panel will, following up on the last theme of building an ecosystem to take advantage of this technology, will be on international cooperation, and in particular, Japanese and US cooperation. We're at a forum here today thanks to NEDO and the Silicon Valley Forum that has brought together an extraordinary group of people from many different parts of this ecosystem. What more should we be doing? I'd love to hear Allison's thoughts on the international research scene. I'd love to hear thoughts about industrial cooperation and then, of course, governmental cooperation as well.
Sure. Well, on the academic side, it is typically quite challenging to do international projects. I'll give one example. We currently have a US DoD and Korea MOTI collaborative program on search and rescue robotics, but there has to be a decision separately on the US side and in that case on the Korean side to fund, and then that is not a special situation. And almost all international collaborative research grants that are government funded, it kind of has to be successful twice in order for the whole project to go forward. So that's very challenging. I don't know what the solution is. It's great that federal government, both in the U.S. and elsewhere, are attempting to do these joint projects, but currently the barriers to entry are pretty challenging.
So from the government side, definitely there's a huge amount of opportunity for international cooperation, especially in the area of search and rescue and first responders and robotics in particular. I don't know of any specific bilateral agreements in place where this is an area of focus, but I do know that in the work that I do, where we're looking to find startups that have great talent, I'm able to fund international companies, not just U.S. companies, and so where there are opportunities, I've talked to a number of international governments that are interested in, potentially co-funding or sending startups to our opportunities. So I think the opportunity is endless there, and certainly we are creative about finding new ways to try and figure out how to do either co-funding, and not so much in the traditional sense of joint grants per se, but where other government agencies are looking to do something along the lines of what DHS and DoD have done as far as funding startups and figuring out ways where international funding can go towards either international startup funding or towards our program. We're definitely open to a lot of new ways of figuring out how to do these joint programs, formally or informally.
Would anybody else like to comment before we turn to audience questions?
Actually, from industry, we are doing only for Japanese market with maybe Japanese. We have a lot of collaboration with Japanese university. However, now we are very open to collaboration with non-Japanese university, but U.S. university and including startup companies. And also, we are now talking U.S. big companies, corporation, about robot. So we found that there are a lot of potential customers. They want to have a kind of special robot, and their main business is not making robot. So they were happy to buy the kind of special robot if we can provide with a reasonable price. So from industry point of view, we have a lot of potential collaboration with U.S. corporate and Japanese corporate, maybe Japanese corporate and U.S. government or vice versa. Yeah, so we have a lot of potential collaboration with U.S. and Japan.
Well, thank you. And with that, we have about 10 minutes left before our time here is going to come to an end. I'd love to hear a question for the audience. Do we have any? Yes.
You can hear. I'm quoting the real case situation. The first case is the recent wildfires in Northern California, which destroyed the 6,000 buildings and the wine industry. So this is like a very disruptive wildfire. So how the applications of robotics and drones helped in the for these wildfires, and then for the for the application here. And then the second case is about the 2011 the Fukushima nuclear disaster, and this one it is preventable. But then for this disaster, how as Mr. Masato said, robotics can help in for the nuclear plants also. So how can robotics future in for the prevention and for the application for the disaster like that? Thank you.
Great. Why don't we start with Fukushima?
Yes. We are developing a robot for, actually it was not intended for Fukushima. We started developing that kind of robot maybe over 10 years ago. And eventually we applied our robot to Fukushima plant. And it did a great job for picking samples or something like that. And it's a very difficult to answer, but how to maintain that kind of robot regularly, that is very difficult. Of course, the robot itself is difficult. However, probably we have to keep operator for maybe next incident. So that kind of problem is very difficult, how to solve it, yeah.
I'll just throw in a comment from my own experience. I was an official in the Department of Defense when Fukushima happened. And I remember watching people make very difficult decisions about whether helicopter crews should fly search and rescue missions in certain areas around the nuclear plume, whether the crew would be exposed to too much radiation. And it brought to mind immediately how wonderful it would have been to have a far more robust suite of robotic search and rescue tools for a nuclear disaster. Does anybody want to answer or approach the first part of the question, or do we want to sneak some more questions in?
I don't have a specific answer to how to have prevented any of the California wildfires, but I do know that from one of the funding opportunities that we have is to specifically come up with solutions for 3D dynamic mapping for first responders, particularly firefighters in buildings, and so the ability for potentially robots to help firefighters that are in buildings be able to dynamically map the structural changes of the building, I think hopefully introduces new opportunities for robots that can actually sustain certain temperatures that would be in a fire situation, and that hopefully can also be a bridge to additional technologies or solutions that could be deployed in situations like the wildfires.
All right, our next question.
Hello, my name is Suyash. Really fascinated and learned a lot today. My passion is in animatronics and social robots. My question is, since robot is such a, it's just kind of a scary technology in one way, how to make it more friendly and how to develop a really nice user experience. Could anybody talk about that? Just the design, because a lot of them I've seen, they kind of look either ugly or scary or not engaging enough, and that affects how you interact with it. So if you could talk about the better design of the whole user experience, or just the industrial design, or UX of the robot.
I can address that a bit. So a lot of the work that I'm involved in is in human-robot interaction, mostly in my case in terms of the physical interaction and how do you make that interaction safe. I think for a lot of these field robots, right, if we're going out in a search and rescue scenario, currently the focus is really on the technology and just getting it out there. But absolutely, if you're coming across a frayed disaster victim, an elderly person or a child, how the robot can interface with them, not just the user who's driving it, but the person that we're attempting to rescue is going to be important. We've heard many stories from the wildfires about people having to be convinced to leave their homes. There's a social component to keeping people safe. So I don't have the answer about how to do that right, but there is a great amount of research going into how to make robots more expressive, and whether it should be very explicit or should it be done by giving the robots human qualities. And we don't think we have the answer yet. There are a lot of interesting, I think, studies to be done that range from psychology to neuroscience, going far beyond the robotic technology. But that social interaction is going to be key to making robots successful, even in these sort of field robotic scenarios where people might not think to make this connection that you have made to social robotics.
Thank you.
We have just a couple minutes left. Are there any last questions from the audience? Well, I guess I will then take the moderator's prerogative of asking the last question, and I'll actually ask it to Allison, who has shown us a little peek at what the future may be in this area. But I think, as we've seen from all of the panelists, it's going to be very hard to realize that feature to its fullest, because this really is a complex environment. So I would love to ask Allison if she could just sketch for us how difficult it is to make her robots work. How many research hours, how many graduate students, how many false starts, how many months to get to those amazing videos that we saw of robots able to snake through small spaces and turn valves and do just amazing things that you can intuitively grasp would be critical in a disaster situation.
Yeah, that's a great question. And I have to say that I think this particular project that I've shown is much more accelerated compared to traditional robots, in part because of the accessibility and the quick sort of manufacturing techniques. This is the kind of prototyping with popsicle sticks and plastic, on the lab bench. But in any case, what I showed is about 2.5 years from initial conception of the concept to getting to this point where we have good demonstrations in a laboratory environment. And I think it's going to continue to be difficult to move it forward as we put it in the field. But that said, there are definitely different types of technologies, some which can be accelerated more quickly. I'm a mechanical engineer, so in some ways I'm very jealous of my more computationally oriented colleagues who can do algorithms and hit, restart if something goes wrong. Mechanically, in terms of developing these robots, something goes wrong, it can actually be months of additional development to get a new prototype working again. And so the advantage of soft robots has been that we can actually do that cycle quickly. But I think these more traditional robots, I talk about the hours in my laboratory, but I imagine that the products at Mitsubishi and some of the examples that were shown from NEDO, those are many more years and person hours in the making than the kinds of things that I've shown.
Well, on that note, I would really like to thank my fellow panelists for taking all of us on a tour of this fascinating area. And I would also like to thank everybody in the audience for sticking with us at the last panel of a very, very full day. So with that, we will make our exit and turn the stage over to the closing address.